Have you ever wondered why your coffee cools down, how engines work, or why ice melts? The answer lies in thermodynamics, a science that helps us understand heat, energy, and how they interact. Today, we will explore the scope of thermodynamics, thermodynamic properties and equilibrium, where it is used and how it helps us in different fields. Where is thermodynamics used? Thermodynamics is everywhere. It applies to small things like the movement of tiny molecules and big things like how power plants generate electricity. Scientists study thermodynamics on two levels. First is microscopic scale. This level looks at tiny particles like atoms and molecules. For example, in chemistry, scientists study how heat affects chemical reactions and how molecules behave when energy is added or removed. Second is macroscopic scale. This level focuses on things we can see, like temperature changes, pressure, and energy flow. For example, in engineering, thermodynamics helps design engines, refrigerators, and air conditioning systems. We have here a table of microscopic and macroscopic approaches to describe their certain differences for better understanding. Broadly speaking, we see thermodynamics in two different views of approaches. The microscopic, from the name itself, indicates that we go in the micro level, and the macroscopic being on the general level. So, in a microscopic approach, the behavior of an individual molecule is taken into consideration. So here, we study the behavior of each and every molecule. Whereas, in the macroscopic approach, the average behavior of all the molecules is taken into consideration. Here, we don't go for individual molecules. Microscopic approach is also called statistical thermodynamics because here we have lots of data and statistics to deal with. And the macroscopic approach in thermodynamics is also called classical thermodynamics, where it relies on observable properties like temperature, pressure, and volume to define system behavior. A microscopic approach is applied whenever the density is low. In the macroscopic approach, we apply whenever the density is high, or when we have a huge number of molecules. The microscopic approach will give us exact and accurate results because here, we are dealing with each and every molecule, so the perfect result is obtained for every molecule. But in the microscopic approach, since we are generalizing the things, and taking the average, that is why the results will not be that accurate or exact. Rather, it would be approximate, but more or less it will be close. Moreover, the macroscopic approach is more time-consuming, and the macroscopic approach is less time-consuming. Thermodynamics is useful in many fields. Let's look at 3 examples from engineering, chemistry, and environmental science. For engineering example, car engines work by converting fuel into energy using thermodynamic principles. Or refrigerators remove heat from food to keep it fresh. And power plants use heat to generate electricity, providing energy for homes and industries. In chemistry, chemical reactions like burning fuel or photosynthesis depend on heat transfer. Phase changes such as ice melting or water boiling involve thermodynamics, and batteries store and release energy based on thermodynamic principles. In environmental science, for example, the greenhouse effect traps energy in Earth's atmosphere, affecting climate change. Or weather patterns like storms and temperature shifts occur due to energy movement. And ocean currents form because of temperature and salinity differences in water. As you can see, thermodynamics is not just about heat, it is about energy and how it affects everything around us, from cooking food to designing machines and understanding climate change. Thermodynamics is a powerful tool that connects science to our everyday lives.
Extensive and intensive properties in thermodynamics. Have you ever wondered why some properties of an object change when you add more of it, while others stay the same? In thermodynamics, We classify these properties into two groups, extensive and intensive properties. Today, we will explore their definitions, real-life examples, and how they relate to each other. Thermodynamics properties describes the condition of a system. Some properties depend on the amount of substance present, while others do not. Understanding these differences is important for designing efficient energy systems, analyzing materials, and making scientific predictions. Intensive properties. Intensive properties do not depend on the amount of substance present. These properties remain the same, whether there is a small or a large quantity. First is temperature, the degree of heat or cold. Example, a cup of boiling water has the same temperature as the large pot of boiling water. Second is pressure, the force exerted by particles in a system. Example is air inside a small balloon and a large balloon can have the same pressure. Last is density, the ratio of mass to volume. Example to this is gold has the same density whether it is a small ring or a large bar. Intensive properties help identify and describe substances. Scientists rely on them for research, and engineers use them to choose the right materials for construction and manufacturing. Extensive properties. Extensive properties depend on the amount of substance present. If you increase the amount of material, these properties also increase. First is mass. More substance means more weight. Example, a small piece of metal weighs less than a large block of same metal. Second is volume, the amount of space a substance takes up. Example, a large bucket holds more water than a small cup. Third is energy. More fuel provides more energy. Example is, a big gasoline tank contains more energy than a small one. Extensive properties measure how much of a substance is present. Engineers use these properties to calculate fuel efficiency, and scientists consider them when studying chemical reactions. Extensive properties can be used to determine intensive properties. For example, dividing mass by volume gives density on intensive property. Similarly, total energy divided by mass gives specific energy, which is also intensive. This connection helps scientists and engineers analyze materials and design efficient systems. Both extensive and intensive properties are important in science and engineering. Here are 3 examples from daily life. First, in cooking, a large pot of water takes longer to heat, extensive, but the boiling temperature remains the same, which is intensive. Second, for cars designs, engineers consider total fuel energy, which is extensive, but must maintain the right engine temperature, which is intensive for efficiency. Also, in weather forecasting, meteorologists measure total heat energy, extensive, but focus on temperature, which is intensive, to predict weather changes. Understanding extensive and intensive properties helps us analyze materials, design better systems, and improve scientific research. Extensive properties depend on quantity, while intensive properties remain constant. Their relationship allows scientists and engineers to develop efficient technologies and solve real-world problems. Next time you cook, refuel a car, or check the weather, think about how thermodynamic properties play a role in everyday life.
Imagine you leave a cold drink on a table for a while. Eventually, the drink warms up to match the room temperature. This happens because of thermodynamic equilibrium, a state where everything balances out. Equilibrium means balance. In thermodynamics, equilibrium happens when a system stops changing over time. This means no more heat flow, no pressure change, and no further chemical reactions. We have here 3 types of thermodynamic equilibrium. First is the thermal equilibrium. This refers to the condition in which 2 or more objects in thermal contact reach the same temperature and no longer experience a net transfer or heat between them. In this state, the rates of heat transfer in both directions are equal, resulting in a uniform distribution of thermal energy. This concept is fundamental in thermodynamics and is observed in natural and artificial systems, from everyday objects to planets in space when they attain a common temperature. Second is the mechanical equilibrium. It is the pressure in a system stays the same when no force is pushing or pulling. In classical mechanics, a particle is in mechanical equilibrium if the net force on that particle is zero. By extension, a physical system made up of many parts is in mechanical equilibrium if the net force on each of its individual parts is zero. For example, an object resting on a surface and the corresponding free body diagram showing the forces acting on the object. The normal force N is equal opposite and collinear to the gravitational force mg, so the net force and moment is zero. Consequently, the object is in a state of static mechanical equilibrium. Another example is the sealed soda can maintain its internal pressure unless it is opened. Or a book resting on a table. The force of gravity pulling the book down is balanced by the normal force pushing the book up from the table. And lastly is the chemical equilibrium. It is when chemical reactions stop happening because everything has balanced out. For example, hydrogen and iodine gases react to form hydrogen iodide according to the following reaction. Initially, only the forward reaction occurs because no HI is present. As soon as some HI has formed, it begins to decompose back into H2 and I2. Gradually, the rate of the forward reaction decreases while the rate of the reverse reaction increases. Eventually, the rate of combination of H2 and I2 to produce HI becomes equal to the rate of decomposition of HI into H2 and I2 when the rates of the forward and reverse reactions have become equal to one another. The reaction has achieved a state of balance. Chemical equilibrium is the state of a system in which the rate of the forward reaction is equal to the rate of the reverse reaction. Another example is in a closed container, water exists in equilibrium between liquid and solid forms or ice at its freezing point. The rate of evaporation or liquid to gas is equal to the rate of condensation or gas to liquid. Or in a carbonated drinks, once the dissolved gas reaches a stable concentration, no more bubbles form.
In conclusion, thermodynamics is the science that explains how heat and energy interact in different systems, influencing fields like engineering, chemistry, and environmental science. It helps design efficient engines, predict climate patterns, and understand chemical reactions, making it essential in scientific advancement in daily life. By recognizing its role in maintaining equilibrium, controlling energy flow, and shaping technological progress, we can appreciate how thermodynamics connects the physical world to innovation, whether in power generation, refrigeration, or biological processes. Its principles guide us towards smarter solutions and sustainable developments that improve the way we live.